Chapter 3, we will use calculus to analyze important features of graphs of functions. So today we're talking about extrema on an interval. Extrema are maximum values or minimum values. Absolute extrema are one type of extrema we'll talk about in section 3.1. We'll focus on absolute extrema. The maximum or minimum value of the whole function on a closed interval. That word or should not be there. It could be at an endpoint of the closed interval. A closed interval is a new vocabulary word. It means the endpoints are included as possible high points or low points. Endpoint extrema are when the max or min occurs at the endpoints of an interval. So let's look at this function I've graphed over here, negative quantity x minus 2 squared plus 5. If I'm asking for the max on negative infinity to infinity, I'm asking for the maximum y value on the open interval, the whole interval. So a maximum can be the maximum or minimum, the absolute extrema can be the maximum or minimum on the whole interval or the closed interval. So well, that maximum value would occur right here. That's the top, and the y value there is 5. So our max is 5. The minimum on the closed interval, we can tell it's closed because of the brackets, 3 to 5, occurs, here's 3, and here's 5. 3 and 5 are x values. And if I want the minimum on the interval from 3 to 5, I want the lowest y value, so that would be negative 4. So absolute extrema can occur at endpoints on a closed interval. It could occur between endpoints on a closed interval. So if I said I wanted the max between 3 and 5, then I'm looking at this interval from 3 to 5. That max would be at 5. Or an absolute extrema can be the maximum of the whole interval, all real numbers, the whole open interval from negative infinity to infinity. So that's what an absolute extrema is, either the highest or lowest point on the whole domain of the graph or on a closed interval including the endpoints. So the extreme value theorem, don't have to memorize it, it's just something you need to know about. If f is continuous, so let's think about what that means. There's no jumps, no holes, no vertical asymptotes, and no oscillations. So f has to be a function without any of those things, and it's looking at the closed interval, then it has to have both a max and a min. It's kind of logical that a graph would, if it doesn't have anything weird going on, it's going to have a high point and a low point. So here would be nothing. This would be the high point, that'd be the low point. Or even if we have a graph like this, there's a low point, there's a high point. If we have a horizontal graph, they're all high points and low points. If we have a graph that's like this, closed interval, this point's the highest point, this point's the lowest point. So any closed interval, as long as there's nothing funky going on in between the endpoints, it's going to have a max and a min. Relative extrema, different than absolute extrema. It's the max or min on an open interval. An open interval is when the endpoints are not included. So a minimum on the graph from 5 to 8, open interval, endpoints not included. 5 would be here, and 8 would be here. So we're not looking at any other part of the graph. We're just looking at the graph between 5 and 8, but not including 5 and 8. So the minimum value, yep, we've got a minimum value right there. So we do have a minimum value. It's about 263. The maximum value, we try to get up to the highest point, which looks like it might be around here, but we can't get there because that point's not included. So there is no maximum, between 5 and 8. But if we look for the maximum value between 3 and 5, so we're looking at a different interval now, 3 and 5, we do have a maximum on that interval, but the interval from 3 to 5 would have no minimum. So this would have no max, and this would have no min. So with an open interval, you're not guaranteed to have a max and a min. You might have neither. neither max nor min. If we had a graph like this, the endpoints are not included, there's no high point, there's no low point. So that graph would have neither a max or a min. So here's an example of a graph with no min, but it does have a max. Here's an example of a graph with no max, but it has a min. This has both a min and a max because it's a closed interval and it's continuous in between, so it has both. It's guaranteed to have both. And this is an example of a graph that has neither a min or a max because this graph goes up and down forever to infinity. So what we're going to try to do today is figure out where those maxima and minima occur on a graph without looking at the graph. Well, the only possibilities are when the graph has a horizontal tangent line, or if there's a cusp or a jump, or it could be at the endpoints for absolute extrema. When we're looking for a relative extrema, we won't have endpoints. So looking at a graph, it could be easy to see where the maxes or mins are, but how do we know algebraically if there's going to be a horizontal tangent or a jump or a cusp or anything? Well, we can analyze our derivative because horizontal tangent lines are when the derivative equals 0 and cusps and jumps occur when the derivative is undefined. So the places where relative extrema could possibly occur are called critical numbers. The definition of a critical number, first of all, f has to be defined at C. So if f is defined, that means that we're not talking about where there's a hole or where there is a jump or where there is an oscillation or where there's a vertical asymptote. So f has to be defined at a point C, but if that point has a derivative that equals 0, then it's a critical number. Or if that point is not differentiable, so then that could mean it has a cusp or a vertical tangent, then C is a critical number. So basically what we're looking for is where the derivative equals 0 or where the derivative is undefined. Algebraically, let's go back and just talk about that. So algebraically, when the derivative equals 0, if we have a fraction, which part of the fraction has to equal 0 for this fraction to equal 0? The top has to equal 0. If we have a function whose derivative is a fraction, we've got stuff up here, stuff down here, when will this function be undefined, this derivative be undefined? It's when the denominator equals 0. So we're going to look at our derivative and analyze where the top equals 0 because that's going to be horizontal tangents, or where the denominator equals 0 because that's going to be our cusps and vertical tangents. Theorem 3.2, another theorem that's good to know. Don't have to memorize it, just know about it. Relative extrema occur only at critical numbers. So if a function has a relative max or min, it's only going to occur at a critical number. In order to find extrema, which is what we're going to focus our assignment on today, is finding extrema on a closed interval. First, you find the critical numbers. So you take your derivative, and you find out where it equals 0. So that's where the top equals 0. You also take the derivative and find out where it's undefined, which means where the denominator equals 0. Those are going to be C. Those are critical numbers. Then we plug C into the original function because that's going to be our y value. So plug those C values you got from setting your derivative equal to 0 and looking where your derivative is undefined. Set them, or put those values into the original function to find the y value. Also put in the endpoints to the original function to get the y values at the endpoints. And then you look for the highest or lowest numbers. The highest will be the max, the lowest will be the min, so you're comparing all those y values you just found. So let's do an example. 2x minus 3x to the 2/3. First we're going to find the critical numbers on the interval from -1 to 3. So we have a closed interval. So keep in mind that we have to check our endpoints too. And then we're going to find our extrema. So first we're going to find critical numbers, so we have to take the derivative. And I do want to find where that equals 0, so I'd like it to be one fraction, because this part is really written like that. So I can get a common denominator, or I can just look at it as is, but it'd be better to get a common denominator. So I'm going to multiply this by x to the 1/3 over x to the 1/3. So I have 2x to the 1/3 minus 2 all over x to the 1/3. That's the derivative. And I want to find c. So I want to know where it equals 0, and I also want to know where it's undefined. Wherever a fraction equals 0, it's where the numerator equals 0. So I'm going to just solve this to find where the numerator equals 0. Add 2 to both sides. Divide by 2. And x to the 1/3 equals 1. So cubing both sides to get rid of that 1/3 power, I get x equals 1. So c is my critical number at 1. C is 1. Another critical number occurs when the denominator equals 0. That's where the fraction's undefined. Again, cube both sides and you get x equals 0. So my critical number is 0. So I have two critical numbers, 1 and 0. Those are places where I could have a max or a min. So then if the next part says find the extrema, let's just look at the graph for a second here. So you see at 0, we have a critical number because what's going on there? Remember, 0 came from where the denominator was equal to 0, so the derivative's undefined. There's a cusp there. So that's a possible max or a min. And then at 1, possible max or a min. Let's go back and check our critical numbers in our interval. Are 0 and 1 in the interval from -1 to 3? Yes, they are. So then we have answered our first question. Find the critical numbers on the interval from -1 to 3. And we confirmed it with a graph, which is unnecessary, but just so for learning purposes, we want to do that. Then we want to find our y values at those critical numbers. So we're going to plug 1 into the original function. Plugging 1 into the original function up here, f of 1 would be 2 minus 3, so that equals -1. F of 0 would be 0. Then we need to check our endpoints. So plug -1 into the original function. We get -2 minus 3, which would be -5. And then plugging 3 in, we'll get 6 minus 3 times 3 to the 2/3. Need a calculator for that one. -0.24 or something, approximately. We're going to use 3 decimal places. So to find our max, we want the highest of these y values. Looks like this is our max. And yep, it looks like a max to me. And then we want the lowest y value, -5, -1, -5. So that's our lowest. So that's our min. So the max occurs at 0, 0, and the min occurs at -1, -5. This is a relative min. It's lower compared to the points around it, but in the interval from -1 to 3, so in this interval, it's not the lowest point. So it's not our extrema. Here's your homework, 1 through 41 every other odd, and 55 to 59 odd, and 65, 67, and 68. For number 29, you'll need to take the derivative of the absolute value. You can separate it into the two functions, the piecewise functions, or you can use this derivative formula. You don't have to memorize this derivative formula, but just be able to use it. So the derivative of the absolute value function is u over the absolute value of u, and u is whatever's inside the absolute value, and then times the derivative of what's inside that absolute value. All as long as you're not taking the derivative of 0. You don't have 0 in the denominator here, so u can't be 0. All right, have a good night.